We are now going to discuss the central limit theorem for sums. So much like the central limit theorem for means, for sample means, we have the same kind of idea and requirement of as long as your sample size is big enough, the distribution for these will turn into a normal distribution with some adjusted mean and standard deviation. The mean, now we're going to be talking about the sum of x. That big sigma we discussed back in chapter 4 about the sum of something, we're going to bring that notation back. So when I read this, it's the mean for the sum of x. And we're going to have a new standard deviation for each of these as well. So number-wise, our mean is not going to be the same anymore because now we're going to be talking about collecting 35 pieces of data and adding them all together. So if I was talking about the age of students in a third grade classroom, all right, I was talking about the age of students in a third grade classroom. The average age of a third grader, which don't laugh at me if this is really far off. I'm trying right now to do the math. A third grader would be what? 10? No, maybe less than that, right? 8. Geez, we'll say 8. Sorry if that's really off. The average third grader would be 8, but I'm not talking about 8 being the piece of data. The average for the sample sum would be, let's say, 38-year-olds, 7, 8, 6, whatever. We're adding all of those ages together. That's the average that now needs to be in here. So this needs to be a much higher number than the actual average that's originally given, because we're talking about the addition. We're talking about the sum of all of our data. All right, so again, unlike sample means, that mean in the middle is not going to stay the same as whatever mean they give you to begin with. And the standard deviation is also going to change, but it's going to change in the other direction. It's going to get much bigger because when you're talking about adding data together, that data becomes much more spread out on where that average lies, that middle point lies. Okay, so let's talk through the official definitions. Again, the idea is the same. You're drawing these random samples of size n, and as increases the sum of x, that's how we're going to write it. That's what I wrote up here. This is the mean for the sum of x, which consists of our sample sums. It tends to be normally distributed. That part is the same. We are still looking at a normal distribution with a mean of, and this is where our mean actually gets to change. Our mean is going to be the old mean times n. All right, a little bit different there. We have our old mean, mu sub x, and we're going to multiply that times n. So you can write that as a dot. You could write it in parentheses next to each other, whatever works for you. It's a multiplication. That's going to be the updated mean, and the updated standard deviation is also a multiplication. It's the old standard deviation, and now it's times the square root of n. Still involving a square root, but now it's a multiplication of the old standard deviation times the square root of n. So written with our distribution notation, we have the sum of x is normally distributed with the old mean times n, comma, the old standard deviation times the square root of n. Those would be the two numerical values that would describe our new mean, or the mean for the sum of x, and our new standard deviation, or the standard deviation for the sum of x. I won't write this notation too frequently, the sub-index looking thing, but that's what that sub-index is representing. This was the original distribution, mean and standard deviation. This is the mean for the sum of x. This is the mean for the standard deviation for the sum of x. The z-score has that same kind of idea. Remember, the z-score was equal to the data value minus the mean over the standard deviation. So here, our data value was the sum of one specific sample. We would be subtracting out this new mean we just calculated, and we would be dividing by this new standard deviation that we just calculated. So it's taking that old concept, but we're just replacing each piece with our new piece of information.